Welcome to Study Loop.
Problem 8.105. So here we're going to do a bit of calculus to find the center of mass of this semicircular plate. We've got a radius A, some thickness T. We're told X and Y go like this. We're helpfully told what the total mass of the disk is, so we don't have to go to the bother of figuring that out ourselves. So let's write down a couple of preliminary things we're going to want. We know that the center of mass is the weighted average of the position of, an entire system weighted by the mass. So in a continuous case, an average is 1 over the sort of interval that we're looking at. This would be times x dm. And then similarly, the y-coordinate of the center of mass is 1 over m times the integral of y dm, where this is the infinitesimal mass of, whatever elements we're looking at. And then we're also going to want to know the relationship between x and y at the surface of the plate, because here it's a straight line, so that's, fine to deal with. But since this is a circular arc, then the equation for a circle applies, where basically the distance from the origin has to be equal to the radius, or squaring both sides. The sum of the squares of the components of the position vector have to be equal to the radius squared. So now let's start thinking about the x-coordinate. First off, since there's an equal amount of mass on either side of the y-axis, we're hoping to see the x center of mass, the x-coordinate of the center of mass is going to be 0. It should be in the middle here, because if you flip this around so that x goes to negative x, it looks exactly the same, so the only place the center of mass should be is at x equals 0, or along the line x equals 0. Y will be more interesting because it's not a complete circle, so it actually does change when you flip it around. And so we have to actually do a little bit more work. So for x, we want to think about dividing this into little vertical strips that have a height of y, width dx, and obviously their position is x. So just taking this equation here, y is always going to be as a function of x, the square root of a squared minus x squared. So plugging that into here, and also noting that dm, which is the mass of this little strip, is going to be equal to its volume times its density. And so now what's its volume? It's going to be, all right, yeah, that's what we need the height for. So, sorry. So it's going to be the density times the thickness times the height, which which we know in terms of x is a squared minus x squared times its width, which is dx. And so now this is going to be the integral from x equals negative a to a of, well, let's put the constant stuff out in the front of it. So rho and t are constants. So rho t over m from x equals negative a positive a of x times the square root of a squared minus x squared. Now, this is an odd function. We can see that because this part is even. If you take x to negative x, this doesn't change. But this is odd because x to negative x, you know, it changes the sign to negative x. And so an odd function times an even function is odd, and we know that if we integrate an odd function across an interval that's symmetric about the origin, then, you know, this works out to be 0. And like we said at the beginning, this is what we were hoping to get. So all is well with the world so far. For the y center of mass, we want to integrate these little dy strips. They have a width of 2x, and then the thickness is, of course, t always, and then dy is their height. So here our dm is going to be rho times the thickness times 2x, the width, which just solve this one for x now, a squared minus y squared, square root of that, and then the height is dy. They just change colors here because it's getting a little bit crowded. So the y coordinate of the center of mass is going to look quite similar to what we just did, except there's a 2 here. Now y only goes from 0 to a. We have y times square root a squared minus y squared dy. So you can use a u substitution to solve this integral, which we're not going to walk all the way through that, but just to tell you what the substitution is you want. If u equals a squared minus y squared, conveniently gets rid of this problem here, then du is going to be negative 2y dy. So this is a substitution you want to use to evaluate this. And working through all that, you'll find that this is 4a divided by 3 pi is our y coordinate for the center of mass.